Good morning. I am Shankar, Alegaon, Professor and Department of Pharmaceutical Chemistry, Kelly College of Pharmacy, Belagavi. Today, I am discussing about interpretation of organic compounds by FTIR spectroscopy. And I have taken today simple aldehyde carboxylic acid. Why FTIR? FTIR is one of the best technique and excellent technique in a pharmaceutical analysis and in a analytical chemistry because it is very easy to use and sensitive and time saving. And also it can detect the wide range of the functional groups like if you say alkane, alcohol, aldehyde, ketone, carboxylic acid and its derivative, amine and its derivative. Most of the functional groups we can detect from the FTIR spectroscopy. And why FTIR spectroscopy has taken in the lion's share in a pharmaceutical industry? Because FTIR, it can give the wide range of the application in a basic drug research and structural elucidation of the pharmaceutical and organic the compound. The second one is formulation development and the validation technique. Third one is the quality control, the process for incoming and outgoing material. Then come to, we can understand the simple basic theory. What is the minimum requirement of any one compound should show the I? It is nothing but about whether any compound which can absorb or which can show the IR spectroscopy. That is nothing but, we can take the simple one example, that is in a carbon dioxide. Carbon dioxide can show the two stretching. One is the symmetrical stretching, another one is the asymmetrical stretching. If you see the in a symmetrical stretching and asymmetrical stretching, what is the common and what is the non-common? If you take the symmetrical stretching, there is a dipole moment is equal to 0. That is means there is no change in a dipole moment. But if you consider in asymmetrical the stretch, there is a dipole moment is not equal to 0. That because there is a something dipole moment in a asymmetrical stretch. Therefore, if you see the symmetrical stretch of carbon dioxide is IR inactive and the asymmetrical stretch of IR is active. So this is the major difference between the, when you take in a carbon dioxide is a simple, that is the 1340, even it's showing it is the IR inactive, whereas in a 2350 reciprocal centimeter asymmetrical stretch, it can show the stretching vibration because it's a IR active. Then come to, there are two important in a vibration technique what we are going to understand in a FTIR spectroscopy, that is stretching and bending. To understand in a stretching and bending, we can take a simple in a spring. Okay, so this spring, how it acts. So one is the stretch. So one is the stretch. The stretch means we require a lot of energy. Then second one is the bend. So bend is required less energy. That's what one is to understand stretch, and second one is the bend. Same only we are discussing about when you see the stretching, there is a change in a bond length. And once again, stretching is divided into two parts, that is a symmetrical and asymmetrical. One is the parallel, another one is the alternative. Then come to bending. The bending is divided into the in plane and out of plane. And this in plane and out of plane is subdivided into okay. If you take in another sense, there is a in a fingerprint region, Why there is a fingerprint region? In a fingerprint region, here most of the some assignable in a peaks are there. And these peaks, it is a difficulty to assign if you are not taken in a standard condition. And usually in a fingerprint region, it starts the 1400 to 700 reciprocal centimeter. If I understand around 3600 to 1500 reciprocal centimeter, it is a very assignable peaks we can get, and around 1400 to 600 or 700 reciprocal centimeter, that region we can call as a fingerprint region. Okay, then apart from this, if you want to understand the spectrum of the IR, one should know what are the different types of the peak I'm going to get. So one peak like a weak peak, second one is a medium peak, and third one is a strong peak. Along with this, there is one more peak, that is a broad peak. That also we are discussing about today. Why I kept in a separately. In one of the section, we are discussing about the broad peak. Next come to, we are starting about interpretation of aldehyde and ketone. And when you say what is the major difference between the aldehyde and ketone, to understand this, the one should know what is the exactly structure of aldehyde and ketone. If you see the aldehyde and ketone, so both common is in a carbonyl carbon. If you see the both carbon containing the carbonyl carbon, but if you see in aldehyde, there is a carbon and hydrogen, there is a one band is there, and whereas in a ketone there is a carbon which attached to the another carbon is there. How it is different? When I say this, so if you take this simple model of the carbon, it is a sp3 hybridized. It is a sp3 hybridized, and another one is then when I say it is a sp2 hybridized, it's a sp2 hybridized. So this is the major difference over the if you compare to aldehyde and ketone. Apart from this, we are not discussing. That is if you see, this is the another one. There is a 180-degree in a sp hybridized. Okay. Just now what I told, in a aldehyde which containing sp2 hybridized, whereas ketone it containing sp3 hybridized. And to understand aldehyde and ketone, we require to understand C double bond O stretch. The basically we can call it as a polar group. And second one is there is a CH stretch in a aldehyde and COH stretch in a acid. Let us now compare the one in a model spectrum. If you take acid, that's what I told you, in a carbon which attached to the OH group. If you take the in a simple spectrum of the aldehyde, what I am going to get? So I am going to get, there is a carbonyl carbon stretch somewhere around 1720 reciprocal centimeter, and second stretch which can assignable is the CH stretch somewhere around the 2800 to 2700 reciprocal centimeter. These are the two characteristic peak along with the other peaks. If I am having the here, it is a, if I take in a simple aldehyde which containing alkane and aldehyde, along with the alkane stretch, I am going to get these assignable aldehyde peak. If I say this is the CH stretch of saturated, that I am going to get around somewhere around 2800 to 2900 reciprocal centimeter, and the characteristic peak of CH stretch, that is a 2720. This is the CH stretch of aldehyde. And second one is the very important one, is a carbonyl carbon stretch that I am going to get in a 1720 reciprocal centimeter. What is the one message I am going to do here to understand aldehyde? The C double bond O, there is a carbonyl stretch somewhere around 1720 to 1680 reciprocal centimeter. And second one is CH stretch of aldehyde. It will give somewhere around 1700 to 2700 to 2850 reciprocal centimeter. Then compared to, if you take in a comparison of aldehyde and ketone, what I'm going to get in a ketone? Ketone also I'm going to get some 1700 in a 18 reciprocal centimeter, and here also in a 1720 reciprocal centimeter. Both they are in a common. If I take in a carbonyl stretch, aldehyde and ketone, they are going to get in a same. Whereas if you see in a comparison, whereas CH stretch I am going to observe in a aldehyde, that CH stretch I am not going to observe in a ketone. Okay, this is the take home. What is the major difference between the aldehyde and ketone? In a ketone, I am not going to get the CH stretch which is observable at the 2700 to 2850 reciprocal centimeter, which is absent in a ketone. But what is a common at 1720 to 1680 reciprocal centimeter, there is a carbonyl-carbon stretch. Next, come to the acid. Along with the acid, what we are going to understand here also, there is a carbonyl-carbon is a common. And apart from the carbon, which has attached to in a simple aldehyde, there C single bond hydrogen. In a ketone, C single bond carbon. But if you take in a acid, there is a C single bond OH. This is a major difference over between the aldehyde, ketone, and the acid. And here, same once again, we are going to understand C double bond O stretch somewhere around 1700 reciprocal centimeters. Second characteristic peak, there is a broad peak at OH, 3400 to 2500 reciprocal centimeter. If you take simple in hexanoic acid, one example, there is a broad stretch somewhere between the 2300 to around 2400. There is a OH stretch, and it has merged up the simple alkane CH stretch also. That's what it is very difficult to assign if you are having the moisture content also. In the moisture content of any organic compound, that peak also comes somewhere here only, and it can make you unavoidable condition, whether it is alcohol peak, whether it is a moisture peak, or whether then common peak which I am going to get is the in a characteristic peak at 1711 to 1690. There is a C double bond O, the carbonyl stretch. Then come to what is the take-home message from the today's small lecture. The simple aldehyde, ketone, and carboxylic acid, we can get the stretching of C double bond O, CH stretch, and the OH stretching and bending we are going to get. And group frequency, one should know. The spectral comparison makes the perfect understanding. FTIR should be taken in a standard condition. And these are the references what I have used for my this lecture. Thank you.